Welcome to this video, the 9th video in my series of videos on Georg Cantor's 1895 and 1897 articles on the theory of aggregates and transfinite numbers. Section 9 is titled The Ordinal Type Eta of the Aggregate R of all rational numbers which are greater than 0 and smaller than 1 in their natural order of precedence. Page 123 outlines three properties which characterize the ordinal type eta of the aggregate R. The second and third characteristic properties, namely that R has no lowest rank element and no highest rank element, and that between any two elements of R there are other elements of R, are straightforward enough to show. And furthermore, since it's been shown that the aggregate R can be rearranged into the aggregate R0, and R0 are equivalent, then R has cardinal number Aleph0. Page 124 formalizes the three characteristic properties of the ordinal type eta into a theorem. That the aggregate M can be brought into the form of a well-ordered aggregate of type omega is based on the idea that M and omega have the same cardinal number Aleph0. Therefore, from section 1, we know that M and omega must be equivalent, though of course they're not similar, and therefore there must be a one-to-one correspondence between M and omega. Therefore, the element M which is coordinated with the element nu of omega will be denoted M sub nu, and M sub nu precedes M sigma in M0 whenever nu precedes sigma in omega. Note that the one-to-one correspondence between M and omega does not need to be explicitly stated, at least in Cantor's view. The correspondence can be assumed to exist simply because M and omega have the same cardinal number and are therefore equivalent aggregates. Also note that well-ordered aggregates will be properly introduced in section 12, although they've already been mentioned on page 115. The ordinal type and indeed ordinal number omega has also been mentioned on page 115 as well. There's a comment in the introduction which is relevant to the claim that M can be brought into the form of a well-ordered aggregate. On page 62, Cantor is quoted as saying, "Every aggregate of the power of the first class, that is, Aleph0, is enumerable by numbers of the second class and only by these, and the aggregate can always be so ordered that it is enumerated by any prescribed number of the second number class, and analogously for the higher classes. An aggregate that is enumerable is understood to be an aggregate that can be put into a one-to-one correspondence with the aggregate of positive integers. Note that R1 in R is to be correlated with the element M1 in M, and not in M0. The correlation that we require is between R and M. The aggregate M0 contains all of the elements of M. M0 is used merely to help form the correspondence between R and M. Since M0 contains all of the elements of M, and since there must be elements of M which are lower in rank or higher in rank than M1, then there must be a least index I2 for which M sub I2 is lower in rank or higher in rank than M1. If not, then M0 would only contain the elements of M which were either higher in rank than M1 or lower in rank than M1. The elements R1, R2, etc. are not being randomly chosen from R. They are in fact the elements of the aggregate R0, and in the order in which they appear in R0. The R1 chosen to start things off is the lowest rank element of R0. R2 is the second lowest rank element of R0. So just like M0 is being used to help form the relevant correspondence between R and M, so R0 is also being used for this purpose. Note also that R0 contains all of the elements of R without exception. Thus, if and when a suitable correspondence is made between each R nu and an element of M, then there is a correspondence between each element of R and M. The process by which each R nu is correlated to an element of M is simple enough, at least from a theoretical perspective. So a correlation is obtained whereby R1 is correlated to M1, and each R nu is correlated to M sub I nu for nu greater than 1. Note that the sequence of subscripts 1, I2, I3 and so on is not necessarily, and in fact probably won't be, an increasing sequence. The claim is that we have correlated definite elements mi nu of M to all the elements R nu in R, and the elements mi nu have in M the same order of precedence as the corresponding elements R nu in R. This is easy enough to confirm since each R nu has been correlated in the way described to an element of M, but the R nu account for all elements of R. Recall that R0 contains all elements of R without exception, and so all elements of R have been correlated to an element of M. Moreover, by the way that the mi nu have been chosen, they have the same order of precedence in M as their corresponding R nu in R. What about the other direction? this is a bit trickier to deal with, and I'll just clarify some of the points mentioned in the proof. The proof follows an induction argument. Suppose that lambda is chosen sufficiently large so that all of the elements m1, m2 up to m nu are amongst the elements m1, mi2 up to mi lambda of the correspondence. Note that m1 is accounted for, that is, m1 is amongst the m1, mi2 up to mi lambda. This is the base case for the induction. The elements m1, m2 up to m nu are the first nu elements of m0, and recall that m0 contains all elements of m without exception. So if we show that all m nu are amongst the m1, mi2, mi3 and so on, then we can see that every element of m is accounted for in the correspondence derived on the previous couple of pages. We consider the two possible cases, either m sub nu plus 1 is amongst the mi lambda, or m sub nu plus 1 is not amongst the mi lambda. In the first case, there's nothing to do. We only have to really consider the second case. The argument works in a similar way to the construction of the correspondence on the previous couple of pages, where we hunted through the elements of the aggregate m0 for a suitable element to correlate to each of the Ri by choosing, at each stage, the smallest value index amongst the elements of m0. Here, though, we look for a suitable element of R0 to correlate to m nu plus 1. This is obtained by, again, choosing the least value index lambda plus sigma, for which R sub lambda plus sigma has the same ordinal position in R to the R1, R2 up to R lambda as m nu plus 1 has in M to m1, mi2 up to mi lambda. At the risk of stating the obvious, I'll just clarify some of the details of the induction proof which I feel are glossed over a bit. Since lambda plus sigma is greater than lambda, and R lambda plus sigma corresponds to mi lambda plus sigma, then mi lambda plus sigma cannot be equal to any of the m1, mi2 up to mi lambda, and so cannot be equal to any of the m1, m2 up to m nu. In the diagram on the screen, the upper row of dots represents the elements m1, mi2 up to mi lambda, and the lower row of dots represents r1, r2 up to r lambda. A possible position of m nu plus 1 is shown. Consider r lambda plus 1 and assume that r lambda plus 1 does not have the same ordinal position with respect to r1, r2 up to r lambda as m nu plus 1 has to m1, mi2 up to mi lambda. We see that r lambda plus 1 cannot be in the indicated position, since then it would have the same ordinal position with respect to r1, r2 up to r lambda as m nu plus 1 has to m1, mi2 up to mi lambda, which would contradict the minimality of lambda plus sigma. So suppose, for example, that r lambda plus 1 is in the indicated position. Then by the correspondence, r lambda plus 1 corresponds to mi lambda plus 1, and that mi lambda plus 1 has the same ordinal position to m1, mi2 up to mi lambda that r lambda plus 1 has to r1, r2 up to r lambda. If we include both r lambda plus 1 and mi lambda plus 1 in the diagram, we see that in fact m nu plus 1 has the same ordinal position to m1, mi2 up to mi lambda plus 1 as r lambda plus sigma has to r1, r2 up to r lambda plus 1. We can continue this for all mu such that 1 is less than or equal to mu is less than or equal to sigma minus 1. And we see that indeed, m nu plus 1 has the same ordinal position to m1, mi2 up to mi lambda plus mu that r lambda plus sigma has to r1, r2 up to r lambda plus mu for each 1 less than or equal to mu less than or equal to sigma minus 1. And in particular, m nu plus 1 has the same ordinal position to m1, mi2 up to mi lambda plus sigma minus 1 that r lambda plus sigma has to r1, r2 up to r lambda plus sigma minus 1 as claimed. Then since by the correspondence I lambda plus sigma is the smallest index in m0, for which mi lambda plus sigma has the same ordinal position in m to m1, mi2 up to mi lambda plus sigma minus 1, as r lambda plus sigma has to r1, r2 up to r lambda plus sigma minus 1 in r, and I lambda plus sigma cannot be equal to any of the 1, 2 up to nu, then I lambda plus sigma is equal to nu plus 1, and so mi lambda plus sigma is equal to m nu plus 1. Therefore mi lambda plus sigma is equal to m nu plus 1. And so we've shown that if I lambda is chosen sufficiently large so that m1, m2 up to m nu are amongst the m1, mi2 up to mi lambda, then we're able to, if necessary, choose lambda plus sigma sufficiently large so that m1, m2 up to m nu plus 1 are amongst the m1, mi2 up to mi lambda plus sigma, and this completes the induction. This confirms that the correspondence found is in fact an imaging of M and R, and thus M is similar to R. Some of the various ordinal types that are mentioned which involve eta have some nice visualizations, such as 1 plus eta can be visualized as all rationals in the open interval 0, 1 with 0. 1 plus eta plus 1 can be visualized as all rationals in the closed interval 0, 1. Eta plus 1, all rationals in the open interval 0, 1 with 1. Eta plus eta, all rationals in the open interval 0, 2 except 1. Eta plus 1 plus eta, all rationals in the open interval 0, 2. Eta times eta, all points on the interior of the unit square with rational coordinates. Thank you for watching. If you found this video useful, then please hit the like button and subscribe to my channel. You can see more videos on various topics on my channel, and if you have any suggestions for topics for future videos, then please feel free to let me know and I'll try my best to put something together. Don't forget to hit that subscribe button and keep an eye out for new videos being uploaded to my channel.